with Jahi, whose name you see here, so it's now in China, and with all the other people. And so you will see a collage of the two works today. And this is actually a part of what I call an unfinished quest, because when I started doing my PhD, we were seeking a lot of representations of, how can we understand point cloud and so on. And on the way, we looked at local features on point clouds and then registering them, aligning them, whatever, and of course doing much more than alignment, like semantic segmentation or more higher level understanding. So, and this work is definitely has a special place, and that's definitely, the journey is not finished, as I said. So I think it's running out of battery, but okay. So many of the problems in computer vision, when you have multiple. So first of all, we have always multiple views, right? It's very hard that you just have a single image at some point. And whenever we have multiple images, we can somehow relate them with graphs or with usually with graphs. And those graphs carry certain information on the edges. Just pose graphs are a nature of treatment, for example, but there are many other graphs. Should you admit the person?
No, the Zoom organizers are doing development.
Okay, so I will start clicking here. So there are also, many other entities that you can actually have on the edges, such as the permutations, correspondences, and everything, right? So there are scene graphs, for instance. There are relations like that. You can encode really relations like this is, the table is under the monitor and so on. And I will, as I said, present two works. One of them is MultiBodySync, so doing understanding over multiple point clouds where the point cloud is undergoing articulations, or there are multiple objects which are changing places. The other is SyNoRim, which is an extension to the non-rigid case. Okay, I will hopefully cover both if time allows. Okay, so let's start with the dynamic moving scenes, right? It can either be articulated. So articulated is when there's a root object or root part, and there are multiple parts connected to the root part. And at the bottom, you see a multi-body scenario where there are two distinct objects, right? This time, there's no attachment. And we want to solve both of these scenarios where we are observing point clouds, right? And well, we want to basically get this segmentation. And for each of those, we also want to get the pose, and we want it to be consistent and coherent so that we can align everything back onto any point cloud that we want. This can also be a canonical point cloud, for example. And we want to do the same for the multiple. Okay, so let's define the problem first. That is, we are given k point clouds, and there are n points in each one. So unfortunately, n will be constant among point clouds in the beginning. And scene will contain S rigid bodies. So there are multiple parts of the object moving or whatever. And we desire a consistent motion segmentation, right? So a segmentation that stays identical, or that doesn't change if I move between point clouds. So it's really a segmentation of the underlying object. And so we want this to generalize across objects. So we really want to understand the motion and not the object, right? We don't want to overfit on the object. And of course, for each of these parts that we segment, we want to come up with a transformation matrix so that the scene is summarized in terms of rigid motions. Right, so let's begin with the pairwise case. So we are given a source point cloud, right, usually, and there is also a target point cloud. And we have, let's say, 7 vertices here and 2 bodies, right? Now, usually what we do, as all the 3D people would know this probably, we kind of associate correspondence, right? This can be nearest neighbor or this in whatever space. We can do this on features and so on. ICP does that also, right? But well, this is not given, it's just the beginning. We associate those, and these are basically like kind of this is the initial relation between these 2 point clouds, and we can encode this into a permutation matrix, right? Where each of those cells is 1 whenever there's a correspondence in between those points. Easy. And given that, so basically these vectors and vertices, I can basically throw all this piece of information into a neural network. Whatever you pick, it's your favorite neural network, transformer one. We just pick the simplest one, which is PointNet. And what we ask is a rigid transformation per vertex, or per point. So each point is basically voting for the object that it belongs. So and the vote is cast in terms of a rotation, right? You can interpret it that way. So instead of trying to immediately regress, the segmentation and then the motion, we start with this. This allows us to do a nice thing, which is basically, if we look now to the reverse map, we do the same thing, but this time from target to source, right? We see where each point goes, right? And we see the rigid transformation. And under the guidance of this rigid transformation, we can always actually segment which points are moving coherently, right? So which points are having the same rigid transformation, and I can bring that back, right? Cool. Using this information, right? I have motion segmentation. Basically, each arrow is now colored. And I can encode this into a motion segmentation matrix where each pixel is occupied, each of those cells are occupied if these 2 points are moving coherently, right? So it's a segment, that's a matrix that describes which of the points are moving together. Good. So I can speak of that entity. It can be a discrete matrix, it can be a continuous matrix if you want to incorporate some confidence. Right, so we spoke about 2 point clouds and we spoke about 2D. Now we can take this to 3D, right? And let's summarize again the procedure that we just saw. The easy one is estimate correspondences and get the motion segmentation later. Okay, now we have n-point clouds, right? How can I transfer this pairwise idea to n shapes? Well, one easy way to do that is through something called, in general, synchronization. You are probably not familiar with that, but as you know, it's a coordination of events to operate a system in union. That's the formal definition, and it actually comes from. It begins, after the standardization of metric system. People also wanted to standardize time. And this is where it dates back to Einstein and Poincaré. I would say they are the first people who actually considered this problem. But now we have it in computer vision everywhere. Like we have, for instance, camera pose graphs where each vertex is a rotation, and we want to average those over the entire graph. And you also see it in language models, for example, that you want to translate different languages. You seek cycle consistency between those languages. That can be phrased as a synchronization tool. Good. So now let's apply the same idea here, but this time with permutations. What we do is we start from A and we match A to B, right? And then we can also match B to C. And if there's a consistent assignment, then A should be matching to C as well, right? Otherwise, it gives me an error term. It gives me a discrepancy. Good. Now I also know how to do it, and you see that between each point cloud, so we have this entire graph here, right? And each edge is associated with a permutation. Now I can now use this information. Like let's get into the details. I want to recover, first of all, what you see here, this P1, P2, P3, P4. So think about this way. We see these partial observations, and we know that there's an underlying object in this. Okay, and this underlying object has points, and I will call this a universe. And there is this graph, And in that graph, I know the pairwise permutation. So I observed, well, I just computed P1, P12, for example, a relative permutation. I want to recover the absolute ordering. So basically, I want to order all the points such that, you know, in my point cloud, the first points always correspond, the second ones always correspond among different views, right? So we have to formulate this problem in terms of the unknowns. What we will do, we will assume, as I said, this universe and write such a loss function, which is easy. So basically, this says take, you know, one permutation, one absolute ordering, and try to relate another one to it by chaining it by a permutation, a relative permutation, right? And so if I go from one permutation, one absolute object to the other one, I have to go with the group action of the relative of the permutations that's given by the relative term. And I can also associate weights to this, so some confidence on the edge, right? Cool. So this problem, you can, well, there are many solutions. First of all, we just pick one, and that's basically the spectral relaxation. So under the spectral relaxation, this minimization, what you see above, can be phrased as an optimization problem, as you see below, and then that is you immediately see that that's an eigenvector problem, right? And this matrix L here that you see is actually a Laplacian that is computed from relative permutations. So it's a giant matrix, and here you see that each element is a relative permutation, so it's really big, and hopefully it's sparse, and so on. So we need to derive permutation. Well, permutation synchronization for this is known, but the weighted version wasn't known, and we also have to do a motion synchronization to synchronize the motion segmentations, just like we do the permutations. So the details of that and the proof that this actually works are all in the paper, if you want to check. And the source code is available also. And these are all differentiable. Whatever I'm talking today is totally differentiable. Cool. So we implemented this differentiable thing as a layer, of course, in many deep learning frameworks. So you can pick your favorites. And this is good, actually, because now having this block gives us an ability to do a declarative forward pass, right? Where we have an optimization. So that's a layer, differentiable layer. However, it has no learnable parameters, obviously. It solves an optimization problem for you. And you can stick it anywhere in your network whenever you want to do information fusion from multiple views, right? So you can now start thinking about where to fuse the data or where to fuse these multiple views, right? So let's look at the full pipeline, how we do it. So now we are given k-point clouds, and for each one, we compute this flow vector. So, you know, the correspondences, the pairwise correspondences, basically, and we send them in to a neural network to compute the pairwise, well, to infer these, you know, well, basically to compute confidences. Let's put it this way. And of course, flow gives us the permutations as well. Now, I can use this just permutations in a weighted fashion to first do a weighted permutation synchronization. And then I can take the result and send it to another neural network, which learns the motion segmentation this time. Okay, and the output of this is really, you know, a matrix, as I said, which encodes the points that move together, right? And it softly encodes it. And then I can now do another synchronization, which is a motion segmentation synchronization. That would enable this coherence, if you want, among different views, right? Good, such that the segmentation is really the same across different point clouds. Good, so we can always iterate this, right, to refine the result a little bit, and it would look like this. These are the iterations, right? So gradually it refines everything together. Cool. So to evaluate this, we collected two data sets. Well, sorry, we used two data sets. One is known, the Sapien articulated objects. And for multi-body, we use the DINLab dataset, which we collected. And that's not a big dataset, by the way. It's just 8 scenes, 17 objects, and 64 dynamic configurations. These scenes are captured with a Kinect scanner. Right. And you know, the traditional flow estimation on an articulated setting looks like that, which is a little ugly. And you know, our approach recovers it quite well. And here the colors correspond to errors. So the red, the more red, the higher the error. Right. So, you know, when we look at just flow estimation, there are pairwise approaches which also work well. Let's say D part here is 595 in terms of endpoint error. Ours is of course lower, but you know, it's comparable. However, if you go to multi-scan setting now, you know, all of them perform similarly, and it's because there is no consistency. This is so much, there's so much you can do just looking at 2 views. And that's why there's like a 20-point jump immediately, right? So this transfers very well to qualitative results. I would even say it's better to look at those. So if you check this, we see that basically, so NPP is, by the way, I didn't mention about any of these methods. You probably don't know them. But these are, the first 3 are basically flow estimation type of works, which you can use to segment different views as well, and just, you know, show it as it is. And NPP is a handcrafted, not a deeply learned approach, Bayesian method for tracking SE3 dynamics. And it's a beautiful, beautiful paper by David Hayden. But again, you know, in terms of, the paper is great, but in terms of quality, I would say it still underperforms the learning-based approaches. Yeah, so as you see, we can output a consistent segmentation across objects. And this transfers very well to DINLab. And this is, you know, this is a small data set. So we cannot really train on this. Therefore, we just directly show generalization. We understand motion, again, not the objects, so we don't overfit. That's why it actually generalizes. And you see, again, consistent segmentation and coherent motion estimation for all. Now, we can actually apply this idea to deforming objects, but deforming only in an articulated fashion, right? So because we can generalize. We just let's just go to, you know, let's just take any other data set and apply our algorithm. Am I going to get something useful? And if you see, you know, it can, without any information about object parts or whatever, it can output something very reasonable, I think. Of course, you know, let's also solve the autonomous driving challenge. Why not? Because we can. Well, we cannot actually, not great. This example is a cherry-picked and good one. Sometimes it works, but of course there are drawbacks to applying this approach to general scenes, right? And of course I will discuss about them. But before, let's look at what we have done. Let's think about this, you know, huge pipeline, like huge looping pipeline, in terms of what we know in computer vision. So first thing we do in such a scenario, we can input representation. So we are not like in image domain now. In 3D, everything is about representation. So we have to determine something. And second is, how do we learn features, right? How do I architect my neural network? How do I learn features? And then the question comes, where do I fuse information coming from multiple views? Right? And this is the first fusion that we do. And then we have another, you know, motion segmentation, because I need that information as well. I need to take it out of the network. So, you know, it's not reconstruction. We are doing so much more. We are basically summarizing the object or scene with rigid transformations that correspond to different parts, right? So there's an underlying abstraction of this. Right, and then there's in the final thing, there's another information fusion through synchronization, okay? And if you think about the forward pass, That's a little late fusion. But through the eyes of a backward pass, it's an early fusion, right? What you do. What that means is, usually, the closer you are to the data, so to the input representation, of course, the better to fuse information there. However, then you kind of overfit to the object, right? So you become much more object, much more data. As you go to the final layers, you are closer to the task, right? This is where the loss is evaluated, and you start becoming more general. So that's why we can do, for instance, motion understanding across different objects, and it's a it's an art basically. Where we draw the line, where we use that information, right? And of course, there are quite a bit of drawbacks actually in all the choices that we have made here. And first, fixed number of points, like we assumed all the point clouds have basically endpoints. Second, we are restricted to rigid motions. You cannot do deformable understanding. It's not really great in recovering partial observations, also primarily because like all these points that you pick, they have to be somewhat correspondable, if you see what I mean. And we cannot handle large point sets. I mean, we do synchronization, and you have seen this giant Laplacian matrix where each single element was a permutation matrix by its own. And that's why you cannot really scale thousands of points. So we have to be something, we have to do something about it, something smart. And the first thing, of course, let's change the input representation. I mean, we don't need to work with points. What we work with are those functional maps. By the way, who is familiar with functional maps? Just that I have an idea. I definitely know one person here who is familiar. Okay. Cool. So here's the idea. Right now we are speaking of points, right? And their correspondences. And there is, of course, an underlying shape. So S here. There's a shape. And the point cloud is actually a discretization of this underlying continuous manifold. Now, we were speaking of point maps in terms of permutations that would take this discrete set of things to another discrete set of things. But now, and just because of that discretization, we weren't able to scale and not handle partiality and so on. So instead of this, let's express this underlying shape as a linear combination of some basis functions. Right? And here the coefficients are h, and the basis I denote as phi. And this is usually, I mean, people have worked on this, right? This is an established literature, and they take these bases to be Fourier bases. And yes, you can define Fourier bases on shapes because of the spectral analysis, right? With all these capabilities, we know how to do this by now. And it's great. It works great. The good part about this is that so first of all, it doesn't relate points anymore. It relates rather function function. Right? So you have to define a function, scalar or whatever field on the shape, and you will relate those with what is called a functional map C now. So instead of a pairwise permutation, a relative permutation, now you have a pairwise functional map. That is a map between functions. And this map, if you know the basis functions, can be converted to a vertex-based map as well. So the moment you recover the functional map, you can do something to recover the point-wise map as well. Well, it's not going to be perfect, so it's still an approximation, but you can live with it. And the nice thing about it is now there's no, it's just a shape parameterization if you want. But there is nothing said about rigidity, non-rigidity. There's nothing. Good. And let's now try to imagine using these basis functions in a neural network. The key is if I were to use eigenbases, right? That means that my individual basis functions would be orthogonal to each other, right? However, and I would say they have been using computer graphics, non-transfer to computer vision very often. And I think the reason is that computer graphics usually deals with this clean data. And in vision, whenever you go to this real life, it's noisy, partial, whatever, all those things. And that's why these orthogonality assumptions, or the Fourier assumptions, actually, I would call it an assumption, because, you know, who said the Fourier bases are the best bases anyway? Let's do something else. Let's try to learn these bases. And we will do the dumbest thing you can ever think of. We will have a neural network. We will send the points in, and we will let the neural network regress those bases. Of course, I will have a loss function that would guide this learning, but, you know, let's just do it. And then I can have another neural network, which is G in this yellow box, that would now try to guess the function correspondence instead of the point correspondence. The good part is, if I have 100,000 points on this object, I can still live with 40 basis functions. So I will be able to scale. And because these basis functions, you can think of them as, so they are mappings of the functions, right? So they are actually mapping regions of shape to regions of shape. So this notion of point correspondence is lost in a positive remark, though, because you don't want exact point correspondences in practical life. First, they don't exist anyway. So like it's almost impossible to find an exact point in two different point clouds. And the second is, now if I have missing data, because I'm describing the region and not the exact point, I will be able to live with it. Right? So I can handle partiality a little bit. Right? So what we do here is to compute a set of basis functions and solve for an initial functional map using this putative correspondence neural network G, and recover flow vectors from it, which I can really do. I mean, again, I can first convert these functional maps to point-wise maps, and also I can have another neural network basically to do it too, like if I want to take it further. And this is what we have here, this refinement network. So now we have 3 neural networks, right, that actually recover the flow that I want, the vertex flow. Seems a lot, but you know, it kind of works. So let's now get it to an iterative end-to-end pipeline over multiple point clouds, right? So I will have the synchronization in there to fuse, right? So now we just compute a basis for each of those point sets. And then, right, we do it for all, and then find a putative correspondence between all of them. So I to j for each I and j. And then let me assemble my graph again, right? So between each shapes, which are parameterized by basis functions, I have a functional map. I compute those functional maps, and the goal, the question is, how can I solve for a consistent, like for consistent functional maps that would correctly match each of the pairwise point clouds, and doesn't matter if I go from I to j through one path or through another path in the graph. Good, and I can still have this refinement network and all the other things to recover the final flow vectors. And now there's no rigid, right? So everything is non-rigid. Basis functions are general. I have everything data-driven and learned. I don't even have a constraint actually on the nature of the deformation. It's kind of implicitly given by the learned basis as well. And of course, I will be supervising this. Right. So now we solve for everything, and because this is like all the point clouds get a deformation field to, you can say, to some underlying canonical object, right? So I can recover this shape. So I can basically transform all the point clouds non-rigidly to any canonical shape or I want, and it's very easy to pick that canonical thing because you can always take the first point cloud as your canonical frame. Good. The good parts of this, now we have a flow-driven computation of the basis functions. Very interestingly, this goes against a little the notion of you know, it goes a little, you know, in the opposite direction of what mathematics would say. So compared to using orthogonal basis functions, we can have, which are, so orthogonal basis functions, they are independent, right? And you would assume that a minimal set of basis functions required for any problem would be achieved through a an orthogonal basis, and actually not, because I think you know, in this scenario we found that learned bases can actually have less redundance, or you know, can be more general than orthogonal bases, and they can explain the shape with less bases actually. I mean, performance wise also. And now we can handle non-isometric deformations as well. So there is no, because orthogonal functional maps actually implied recovery of isometric deformations. I don't have anything like this. And I can use all this supervision information that I have now to actually train this, like flow, consistency, right? And then all the, you know, Laplacian smoothness, chamfer losses, like everything you can imagine from geometry, you can put there as a loss function. Good. And this is how the basis functions look like. And when we saw this first, we thought that, hey, this neural network is actually trying to form these basis functions on parts of the object. So here you see that red parts are the parts where it has attention. And it's kind of doing object detection, but not, because it doesn't need to do it also. So we said, why not, if you know, if this can actually locally canonicalize this moving objects, why not just try to structure those bases? And what we did is, hey, let's just take a 2D example here. It's the, you know, you see the basis functions. One encodes the y coordinate, the other is the x coordinate, and another is the existence of that object, right? So of that part. So here would be y, x. This is the part I'm interested in, and this would be for the other. So here's a basis function, right? Perfectly vetted basis function. Then I can use this to do stuff. The good part here is that it's actually rigid, right? So I can specialize those basis functions to have a rigidity notion. It's very easy, and then I can now apply it again, for instance, to an autonomous driving problem. Now I don't need to really recover non-rigid shapes. Like it's specialized in that, right? So when we do it, and we check the flow results in an autonomous driving setting that we train on this data, by the way, it's not generalizable. We see that ours, you know, this method actually can perform much better than any flow estimation methods like that. But of course, what you see down there is rigid 3D scene flow is another paper of ours. It's specialized for recovering 3D rigid scene flow. Of course, we are worse than that. But still, it's amazing that without doing anything special, just changing that basis function is enough to estimate a better flow for autonomous driving than, you know, a couple of other algorithms. Okay, so we had this synchronization component also to fuse functional maps. I have talked about it, but never said anything about this. It's actually not an easy thing, and I will show you why. So because we have functions now, right? We have functions on the shape, and they are defined in the functional space. Now we have to have a data-aware robust energy that is composed of two terms. One is the data term, which is really like the synchronization term. So instead of permutations, we have functional maps, and the other is a cycle consistency term of the functions, right? So one is regarding the basis, the other is the canonical functions, and we recover both. So it's an optimization non-convex problem in both of these parameters. So this is what we are trying to recover now, and for that we actually derive an alternating scheme. So we fix H, solve for C, we fix C, solve for H. And it's whenever one is fixed, actually it's the convex problem. Good. So then we can recover non-rigid deformations, for instance, from human subjects, much better than any other method, obviously. Otherwise, I wouldn't be talking about this. So, and numerically also, like we had a lot of accuracy metrics or error metrics, and it's fine in all of them. And we can have you know, just by removing some of the losses, we can have a supervised version or a self-supervised version. Thanks to the cycle consistency, by the way. Whenever you have cycle consistency, it's an easy way to get unsupervised machine learning. So through iterations, of course, we recover the deformation rate, and you can see an animation how these two shapes. You see above, these are articulated. You can recover articulated things, easy because they are deformable anyway, and I don't need to do anything special. And down there, you see non-rigid deformations. Doesn't have to be only those. Sorry. We can go ahead and apply this to animals and other things. And the error usually looks okay in these examples. I can now start applying this general idea to other things. So for example, I can take individual depth scans of cloths, point cloths, and then recover a general cloth model. Or I can apply it to other Kinect scans and objects and so on. Of course, there are limitations. One is definitely topology. We don't take care of this, so there's nothing that will understand topology. The other thing is motion ambiguity, not the object ambiguity, not the object symmetry. I'm talking about motion ambiguity itself. And we don't generalize across datasets that well because now these basis functions are learned early stages on the objects that we train on. So sometimes they don't generalize. So it's fine, right? As I said, this is like an unfinished quest. So we will keep making progress on that, hopefully. Right, and just I have to say it here. So I am starting a new group in Imperial College London. Exactly working on similar problems and maybe more, different aspects of machine learning and so on, and 3D vision. And I will be accepting PhD students. Right now I am. So feel free to apply if you are interested. I'm always happy to work together. And I will also introduce another problem, which is very much related to multi-view. So this is the last thing I will speak about. So usually in computer vision, we try to go from images to 3D, and this company actually does it semi-automatically currently, right? And then once you do this, you can actually get a good documentation of your house, which is usable in insurance, in many other application areas like real estate, whatever, home decoration or renovation and so on. But the thing is that I find amusing is this is what the people who actually model your house produce. That's what you see on the left. And state-of-the-art computer vision, and when I say it's really state-of-the-art, does this. So when I look at these two reconstructions, I see that there's a giant gap between. And one of the efforts that we are putting in is basically to bridge this gap together. Right? Okay, so we also have 2 papers here if you want to check those out. Yeah, thank you. I think I talked over time, although not surprised.